So now that we've handled the case of linear, homogeneous, constant coefficients, and degree 2, let's start relaxing some of those conditions and look at some generalizations. So what are some more general cases that we want to know how to solve? First, remember that we assumed when we were talking before that our roots of our characteristic equation were distinct. So it's possible that they are not. Let's talk about what happens in that case. So non-distinct roots. And what happens is, if our characteristic equation r squared minus c1r minus c2 equals 0 has a double root, then double root, let's call it r. Then our two fundamental solutions. So when we had distinct roots, let me just write this here for now. When we had distinct roots, we sort of had these two fundamental solutions, r1 to the n and r2 to the n. And then every solution was some linear combination of those two things. So if we have a double root, we still have the same kind of setup where there's two fundamental solutions that generate all of the possible solutions as linear combinations. And they are an equals r to the n, as before. But now we also have an equals n times r to the n. And this is another thing that will look very familiar to anyone who knows differential equations. Basically, when you have multiple roots, you have to start sticking in powers of n in front of your r to the n. So let's just check that the second one actually is a solution. That's something that we can just check. So this one still works for the same reason that it worked before. So let's check the second one. And let's note a double root means that we basically know what these coefficients are. It must be that C1 is equal to 2r, because C1 is the sum of the roots, and C2 is negative r squared, since C2 is the product of the roots, and the negative is because we've written it with a negative here. Then, let's see. So we want to show that C1 times an minus 1. So that's an minus 1 in this formula, plus C2 times an minus 2. We want to show that this is equal to an. So that's what we're aiming for. And how are we going to find that? It's just a little bit of computation, plugging in what we know about C1 and C2. So this is equal to, plugging in, we get 2r n minus 1 r to the n minus 1 minus r squared n minus 2 r to the n minus 2. And now we can combine these r's and combine those r's, and actually what we get in both terms is r to the n. So that's 2n minus 1 r to the n minus n minus 2 r to the n. So let's go ahead and factor that r to the n out. It's getting close to what we want, because we want one of these guys, and we've got that. So we have, let me distribute this, 2n minus 2, and then distribute the negative is minus n plus 2. from that term times r to the n. And then these cancel, and this cancels with that, and we're just left with n. And that's exactly what we wanted, because that shows that an is equal to an minus 1 times c1 plus an minus 2 times c2. So that equality shows that it satisfies our recurrence relation. So in this case of non-distinct roots, the general solution again is just linear combinations of our two fundamental solutions. So x times r to the n plus y times n r to the n, where x and y are any constants you like, but let's say real numbers. So that is one way that we can generalize this if the roots of the characteristic equation are not distinct. Another more general direction is degree k 2 or larger. So we were dealing with the case k is equal to 2, but what if it is bigger than 2? So now our equation looks like an equals c1 an minus 1 plus a bunch of terms down to ck an minus k. So this is the last one, so it's degree k. And basically, we do exactly the same thing, exactly the same procedure, except our characteristic equation is now a polynomial of degree k, rather than a polynomial of degree 2. So the characteristic equation is r to the k minus c1 r to the k minus 1 down to minus, let's say, ck minus 1 r minus ck equals 0. So now it's a polynomial of higher degree, but we have exactly the same setup where the roots of our characteristic equation give us fundamental solutions that we then take linear combinations of to find all solutions. So let's start again with the case all roots distinct. So let's call them, in this case, r1 through r sub k. Then, as we said, we have the same setup that the general solution is just linear combinations of r to the n. So x1, r1 to the n, plus x2, r2 to the n, plus xn, xk rather, rk to the n, where xi are constants. So now again, let's see what happens for non-distinct roots. And for non-distinct roots, again, it's basically similar to the n equals 2 case. You just have to keep taking higher and higher powers. So so let's say we have some roots with some multiplicity. So r to the k, I'll write it like this. So here's our characteristic equation. And to say that the roots have some multiplicity is to say that some of the linear factors, when we factorize this, are raised to a power. So the roots are r1 through rk. No, not anymore k. Let's call it, t. Let's call it t. But now we're saying they might have powers. So let's give this a power, not a power. So for example, if we have a square here, that means it's a double root. If we have a third power, then it has multiplicity 3, etc. So let's say it has multiplicity m. Then, basically, when we were trying to write down our fundamental solutions, we have the same setup as before, where we're going to have k different fundamental solutions, but now we don't have enough roots to give us k distinct solutions, so we're going to have to add powers of n. So include n to the q times ri to the n as a fundamental solution for q up to n, basically. So q less than the multiplicity, you take those powers of n. So if the multiplicity is 1, you just take r to the n, so you get one fundamental solution corresponding to that. If m equals 2, you get r to the n and nr to the n. If m equals 3, take r to the n, r to the n, and n squared r to the n, etc. So just take as many powers as you need to get the proper number of fundamental solutions corresponding to that root. Okay, so we've gone over what happens when you have degree greater than 2 and when you have non-distinct roots. So let's try and do an example of all of that. So let's find the general solution of this recurrence relation. an equals 7 an minus 1 minus 16 an minus 2 plus 12 an minus 3. So, same process as usual. The only difference is that our characteristic equation is now a cubic polynomial. And this is a fair difference, just in the sense that cubic polynomials are a lot harder to solve. So that is really the only tripping point, as well as maybe remembering what to do when you have non-distinct roots. But okay, let's write down this characteristic equation. It is r cubed minus 7r squared plus 16r minus 12. So I do want to give a quick tip on how to factor higher degree polynomials. Maybe I'll write it down even. Well, essentially, you can take advantage of the fact that the product of the roots is the last term. So this is what you get when you multiply all the roots together. So in this case, we know that the roots all multiplied together is equal to 12. So the constant coefficient is the product of the roots So test factors to find the roots. So first of all, this will not always work, but it will always work if the roots turn out to be integers. And at least in the problems that I intend to be writing, the roots will always be integers. So this should work without fail for any problems that I will set. And let's do it in this case. I mean, I'm not going to do it out long, but let me give an idea of how it works. Factors of 12 or negative 12. So we want to test plus minus 1, plus minus 2, plus minus 3, plus minus 4, and plus minus 6, and maybe plus minus 12. So it's not a perfect strategy because it's going to take a little bit of checking. But what's also convenient is as soon as you find one root, finding the other roots gets much easier because essentially then you've reduced it to a quadratic. So in this case, I won't do any of this computation, but in this case, these turn out not to work, this turns out to work, and this turns out to work. So it factors as, in fact, it's got a double root, r minus 2 squared times r minus 3. So our first root is 2 with multiplicity 2, and our second root is 3 with multiplicity 1. So let's take a look at what we are dealing with here in the multiplicity 1 and 2 case. We are going to get 3 fundamental solutions, as is right and proper for a degree 3 recurrence. And those fundamental solutions are let me go ahead and write the general solution. So, well, the fundamental solutions are r1 to the n. Well, okay, yeah, let me write it like this. The fundamental solutions are r1 to the n, and r1 to the n, because the multiplicity is 2, and then r2 to the n, which is all we get because the multiplicity is 1. So the general solution is taking linear combinations of these and plugging in our roots. So we get an equals x, r1 is 2, x times 2 to the n, plus y times n 2 to the n, plus z times, our other root is 3, so z times 3 to the n. So this is the general solution of our degree 3 linear homogeneous equation with constant coefficients.